Welcome to the deep dive. We're exploring the cutting edge of large language model development today. Specifically, we're looking at ways to make LLMs smarter at reasoning, not just bigger models. And we're zeroing in on one key area, improving reasoning using sampling at test time.
Right. So when these models tackle really complex problems, think advanced math or tricky code generation, they often generate multiple answers, multiple reasoning paths. That's the sampling part.
Mm.
But the real challenge, as our sources show, isn't just getting lots of paths. It's figuring out which one is actually the best one. It boils down to estimating the confidence accurately.
Okay, so the mission for this deep dive is to get into a new theoretical framework that looks really closely at these sampling methods. And this framework didn't just, analyze things. It seems it actually led directly to designing a new approach, something called reasoning pruning perplexity consistency, or RPC. We want to unpack how understanding errors led to, well, a potentially much better algorithm.
Yeah, to really get RPC, you first need to understand the problem through the lens the researchers used. They proposed breaking down the total reasoning error, the chance the LLM gets the final answer wrong, into two distinct parts.
Two buckets of error. And separating them seems key, right? Because it tells you where improvements are even possible. Let's talk about that first bucket, the one you mentioned we can't really fix just by sampling more.
That's the model error. Think of it as a baseline error for a given LLM on a specific task. It's constant. It really reflects the model's built-in fundamental ability to reason correctly. Basically, how well does the confidence score the LLM assigns itself match up with whether the answer is actually correct? If the model just isn't capable, well, the model error puts a hard limit on performance. More sampling won't help there.
So that model error is like the ceiling. If you hit it, you need a better base model, period. Which implies that all the optimization, all the cleverness in these sampling methods has to focus on the other part.
That's the core idea. The second component is the estimation error. Now, this error changes. It depends entirely on, one, how many paths you sample you're in or budget, and two, the strategy you use to estimate confidence from those samples. It measures the difference, the variance between the confidence you estimate and the true confidence.
I think I'm following. So this framework, this decomposition, it gives you a diagnostic. Is my model struggling because it's fundamentally limited the model error? Or is it struggling because my sampling and estimation strategy isn't good enough the estimation error? And the framework suggests that beyond that fixed model error, the rest is bounded by this estimation error we can target.
Yes. And armed with that framework, the researchers then applied it to the main methods people are using now, and it revealed some pretty significant limitations in both.
Okay, let's start with the popular one, self-consistency, SC. My understanding is it's based on consistency, generate lots of paths, see which final answer pops up most often.
That's the gist. It tends to have a reasonably low model error, which is good. Its results often align well with correctness. But the theory shows a big downside: efficiency. SE uses what's basically Monte Carlo estimation. Its estimation error only shrinks linearly as you add more samples.
Linearly. That
Yeah.
sounds slow.
Mm.
If you want half the error, you need double the samples, double the compute cost. For complex reasoning, that could get incredibly expensive really fast.
It can become prohibitive. Which brings us to the other main approach, perplexity, or PPL. This one is probability-based. Instead of counting votes, it just looks at the internal probability the LM assigns to the whole answer sequence.
And PPL is often talked about as being much faster, right? Does the framework confirm that?
It does, in theory. PPL can achieve exponential convergence for that estimation error. Exponential is a huge difference. Instead of doubling work to have error, maybe just a couple more samples give you a massive error reduction. It could be the difference between waiting minutes versus seconds.
Okay, hold on. If PPL is exponentially faster, why isn't it the default? Why bother with slow linear SC at all? Is the trade-off somewhere else, like maybe that model error?
That's the catch. Despite the potential speed, PPL tends to suffer from a higher model error in practice compared to SC. The raw internal probabilities generated by the LLM often don't calibrate well with actual correctness. So the model might say it's 99% confident, but in reality, it might only be right 70% of the time. That's poor calibration.
So PPL is potentially fast, but perhaps less reliable or trustworthy in its confidence scores. And did the analysis find any other issues with PPL?
Yes, one more critical point. That awesome exponential speed advantage, it can degrade quite badly, especially when the internal probabilities the LLM assigns to the reasoning paths are low. Basically, PPL is only super fast when the model is already pretty sure about its answer. For harder problems, the advantage shrinks.
Okay, so we have SC reliable, low model error, but slow linear convergence. And PPL, potentially fast exponential convergence, but less reliable, high model error. And its speed advantage fades on tough problems. We need something that gets SC's reliability and PPL's speed while also fixing that degradation issue.
That's the puzzle RPC was designed to solve, drawing directly from identifying those three theoretical challenges.
So RPC is the hybrid approach. How does it combine strengths and fix the weaknesses?
It uses two main components. The first is called Perplexity Consistency, or PC.
Perplexity consistency sounds like it's blending PPL's probabilities with SC's consistency idea.
That's a good way to put it. PC integrates the internal LLM probability into the self-consistency framework. Mathematically, it manages to keep the low model error we like from SC so the results stay reliable. But crucially, it simultaneously achieves that rapid exponential reduction in estimation error, like PPL promised. This first step tackles both SC's slowness and PPL's potential unreliability.
Right, that addresses two of the three big issues. We get reliability and speed. But what about the third problem? PPL's speed degrading when you have lots of low probability, maybe noisy samples. Does the second part of RPC handle that?
It does. That's the role of reasoning pruning, or RP. Remember, the speed advantage drops if paths have low probability.
Mm.
So RP acts like a filter. It systematically identifies and removes those low probability reasoning paths before they even get to the perplexity consistency stage.
Filtering out the noise first. Okay, how does it know what's noise and what's signal? Does someone have to set a threshold?
No, and that's one of the really neat parts. It's automatic. RP uses statistical modeling. It looks at the distribution of probabilities across all the sampled paths. Specifically, it models this distribution using a mix of two viable distributions. You don't need to get bogged down in the stats, but what it does is automatically separate the paths into two groups, sort of a high probability likely reliable group and a low probability likely noisy group.
Like automatically sorting the wheat from the chaff based on their probability scores.
A very good analogy. This modeling automatically calculates a pruning threshold. They call it tau-tau. Any path whose probability falls below that threshold into the low probability distribution just gets discarded. This ensures the PC part only works with the more promising, higher probability paths, preserving that exponential speed advantage.
And I imagine the computational cost of doing that statistical modeling is pretty small compared to generating lots more reasoning paths.
It seems to be a very favorable trade-off. A little bit of overhead for the RP modeling saves potentially a lot of computation downstream. Because you've pruned the less useful paths, you often need fewer samples overall to reach the same confidence level. You focus the budget better.
Okay, the theory sounds compelling. Did it hold up when they tested it?
The empirical results look quite strong. They tested RPC across 7 different benchmark datasets. 4 were tough math reasoning tasks, Math, Odyssey, Olympiad Bench, AEME, and 3 were code generation tasks, Human Evil, MBPP, and APPS. A good mix.
Let's talk efficiency first. Did RPC actually cut down the number of samples needed compared to standard self-consistency?
Yes, significantly. On those 4 math datasets, using a specific model called internLM2 Math plus 7B, RPC needed at least 50% fewer samples to achieve the same performance level as SC. That essentially halves the computational cost for the same quality of answer.
Wow, half the cost. Can you give a concrete number from one of those hard data sets?
Sure. On the math dataset, which is known to be very challenging, RPC got an accuracy of 51.16% using just 32 samples. What's interesting is that this score was actually better than SC's best score of 50.57%, which needed 64 samples, twice as many.
Better results with half the samples. That's quite improvement.
Definitely. And beyond just efficiency, they also look at overall performance and reliability. When using the same number of samples, RPC showed an average improvement of 1.29% across all the data sets compared to the other methods. And it also improved the reliability of the confidence scores. RPC achieved lower expected calibration error ECE than both PPL and SC.
Lower ECE, meaning its confidence scores are better calibrated. If RPC says it's 90% confident, it's more likely to actually be 90% correct.
That's the idea. It's not just performing better, it's more trustworthy about its own certainty level.
This wasn't just for math, right? It worked for the coding tasks, too.
Yes, the improvements were seen across both math reasoning and code generation, suggesting RPC is pretty generalizable. It's not just a one-trick pony for a specific type of task.
It really feels like a great example of how starting with a solid theoretical understanding that error decomposition can lead directly to a more principled and effective algorithm.
I think that's the core takeaway here. The whole design of RPC seems to have flowed directly from understanding the limitations revealed by that error framework. It was engineered to hit that sweet spot, get the exponential convergence for estimation error like PPL, while keeping the low model error like SC.
And practically speaking, that reasoning pruning component being automatic is a big plus. You mentioned it models the distributions and finds the threshold itself, so it's hyperparameter free.
That's what they report. No need for users to manually tune pruning thresholds for different tasks, which makes it much more robust and easier to deploy.
Okay, so this RPC method looks very promising for making sampling more efficient and reliable. It really highlights the importance of tackling that estimation error effectively.
It does, and it brings up an interesting point looking forward. We've talked a lot about reducing estimation error through smarter sampling and confidence calculation, like
Okay.
RPC does. But remember that model error, the fundamental limit of the LLM itself. That part is fixed by the current model. So maybe the next big frontier isn't just about sampling more or faster, but about developing entirely new ways to measure confidence, new metrics perhaps that are inherently better calibrated, that directly address and try to lower that fundamental model error ceiling itself. That remains a huge challenge.